All right. So Faraday's law says the EMF induced is equal to negative of the time rate of change of the flux through the wire. Again, if the flux through this loop changes, then you induce an EMF. If the flux does not change, there's no EMF. Okay, so, and you saw that we can change the flux one of three ways: either change the strength of the magnetic field or change the area. Here's changing the area, here's changing the strength of the magnetic field. Or it turns out that the easiest thing to do is to change the angle between the area vector and the magnetic field. And that's what we were doing by changing, by rotating that loop in the generator. Okay. Okay, so here's other demonstrations. So this bulb will light up as long as this magnet is moving. Or you could move the loop and the bulb will still light up. Now, if you expand the area, if you change the area, the bulb will light up. Now, only in this case will the bulb not light up. If you just rotate this thing, the flux through this loop is not changing and the bulb will not light up. Okay. Here's another case. So what this is showing you is here's a current, and what this current does is it produces a magnetic field, and the current produces a magnetic field. So the field is going into the sheet of paper here and coming out of the sheet of the paper here. And if this loop of wire moves parallel to the wire, the net flux through this loop does not change, and no current will be induced. If on the other hand, if you move the loop in that direction with a velocity component perpendicular to the wire, either this way or that way, the flux through this will change and you'll induce an EMF in this wire. Okay, what Lenz's law tells you is, it tells you what this minus sign means, the negative sign means. Okay, so what the negative sign means is, okay, the following. Okay, so if you move this magnet toward the loop, it induces a current in this direction. And when it induces a current in this direction, what this is, when a current is flowing in this loop, it's essentially behaving like a magnet with its north pole in this direction and south pole in that direction. So if you move your north pole in this direction, you're inducing a north pole in this direction, meaning the induced current is trying to oppose this guy, is opposing what is inducing this current. Okay, so it's trying to stop this. So to keep moving, you have to apply a force. Okay, so you have to do work to induce this current. Okay, soon as you stop doing work, as soon as you stop doing work, you're not moving the magnet and there's no current. Okay, so via Faraday's law, what you can do is you can convert other forms of energy into electrical energy. Okay, and that's basically what's happening. Okay, so if you move the magnet in that direction, okay, the induced current is such that this becomes a south pole and it'll oppose this motion. Okay, so you have to apply a force to keep it moving in that direction. Okay, so anyway, Faraday's laws relates induced EMF and change in flux. The negative sign, the interpretation of the negative sign is given by Lenz's law. Okay, so again, polarity of induced EMF is such that it opposes the change in flux that produces it. So if you're increasing flux in this direction, the induced current is producing a flux in the opposite direction. Okay, so that's what that is. All right, a good time to pause again, and I'll let you